Oh, I should be. Let me let somebody else in. If you remember F equals ma, force equals mass times acceleration, where acceleration is equal to force over mass. For the same force, it's the electron that moves very easily. It's 1,000 times easier to move than the proton. So that's normally how we. Did I just lose? Hold on. Okay, no, I didn't lose it. So that's where we get our electricity. I don't know what just happened. I just lost my iPad screen. I'm hoping I'm not losing the internet. Okay, there we go. So again, of the major subatomic particles, the electrons, they're nice and light. They're going to carry a charge. Protons do have a charge, but they are much more massive and they're stuck in the nucleus. Neutrons have no charge, so they don't really carry any electricity. All right. Let's talk about electricity inside of conductors versus insulators. Why are things, what do they conduct electricity and why do some things not conduct electricity? Well, conductors, all right, oops, we talked a little bit about this with heat. Conductors tend to have free charges that are moving about. So this is a little bit of a review of maybe high school chemistry. And remember, you know, when you took high school chemistry, if you did take high school chemistry, they talked about how different things would bond. You have ionic bonds, you have covalent bonds, you have metal bonds. So when we look inside different materials, if you have free positive and negative charges, okay, this is just a very general diagram right here, where the positive and negative charges can move about, you have a conductor, okay? Because what happens is I can put an electric field on this, okay, which will create an electric force. The charges will move around, they'll carry the electricity with them. But in an insulator, all the positive and negative charges are locked in place, okay? They can't move. So if you want to answer the question, what is a conductor versus what's an insulator, all you need to ask yourself is, what substances have movable charges and what substances have their charges locked up? Normally when the atoms are locked in place and the electrons are locked in place, it's going to be an insulator. Okay, so metals, for instance, metals are great examples of conductors. They conduct thermal energy, as we saw before, but they're also going to conduct electricity. All right, so looking at this, hold on. Why is this? Okay, still working. I'm having all kinds of technical problems today. Looking at this, we can see that the positive charges in the metals, they're all locked in place, okay? They're all stuck to where they are. They can't move. But our electrons sort of form this cloud-like object around the different atoms. And they like to hang out around the atoms, but the outer conduction electrons, they're actually free to move anywhere inside this metal they want to. Okay, they sort of drift around, stay close to the metal ions, but they can go wherever they want. Okay, and because of this, if we put an electric field on this, the electrons will wander in whatever direction we push them. So when you turn on a light switch, you're letting the electric field get into the metal. That electric field allows the electrons to move, and they sort of just make their way down the wire, carry the electrical energy with them, carry the electricity with them. They're good conductors. Of the best conductors, not surprisingly, those materials that were good thermal conductors are also good electrical conductors. Silver and copper, even gold and aluminum, make really good electrical conductors because they have a lot of free electrons that can move about. Other metals aren't as good, okay? Iron, for instance, is actually a good conductor as materials go. But as metals go, it doesn't have as many free electrons as some of the other materials right here. So generally, its conductivity will be a fraction, maybe 1/6 of what silver and copper will be. So typically, when we make wire, silver is very expensive, gold is very expensive. We're not going to make our wire out of silver or gold. They're precious metals. We'll typically make our
copper.
Copper, our conductors out of copper, which is still very expensive. But if we even want to carry more electricity, where we need a much thicker wire, we'll actually make those out of aluminum because aluminum costs much less than copper. It's a much lighter material. The main concern that we have with using aluminum is it tends to fracture easier than copper. It's not as malleable. It also forms an oxide layer. So inside your house, most of it will be some alloy of copper, okay? For the service into your house, they'll use aluminum where they can use thicker wires and get a much better connection there. So metals, great conductors. Electrolytes are actually good conductors. Believe it or not, water is a terrible conductor. If you have distilled water, it's actually a good insulator because water is a covalent material. But water is also polar, which means I can get in it, or I can dissolve in it positive and negative ions, okay? The water that you get out of your tap, the water that's in a lake, the water that's, especially in the ocean, has a lot of dissolved minerals in it. These are electrolytes. The most common electrolytes are the sodium and chloride, but you'll have things like calcium, you'll have magnesium, you'll have iodine, all these different ions. So generally, you're told always be very careful in a wet location, because in a wet location, if you're in contact with water, not the water molecules, but the electrolytes inside them are free to move about, and they can conduct electricity very easily. So wet locations, we've got to be very, very careful with the devices that we use. Plasma is also a very good conductor. Plasma is not something that we come in contact a lot with. Any spark is plasma. If you ever do any welding, arc welding uses an arc of plasma to conduct the electricity and heat the metal to its melting point. So again, metals are good conductors. Electrolytes are good conductors. Plasma is a good conductor. In all of these, we have free charges that are able to move about. So we don't always want electricity to be conductive. Sometimes we want to block it from being conductive. And that's where insulators come into play. We want to be able to prevent the electricity from escaping our conductors. So oftentimes we'll use insulators to prevent that. Here we can see glass insulators, which are on an old power pole. This might actually be even a telegraph line. Well, a signal line. These are the old glass insulators that you see along the railroad for the signal lines. But more commonly, we'll use things like hard rubber, plastic, and ceramics, because all of these are covalent materials where inside the materials, all the electrons are used up. So remember the metal where the electrons were able to move about? Here, the outside electrons are pretty much stuck to create covalent bonds between the atoms, okay? The atoms can't move, and they're not even charged, so they can't carry charge with them. The electrons are stuck. So with covalent materials, again, things like ceramics, things like rubber, wood is made of cellulose, which is a covalent material. All of these are good insulators and will not carry electricity. So when we think about a wire, typically with a wire, you have your insulator at the center of it, okay? So you've got an insulating wire, which will be some type of metal. And then surrounding that, you'll have the conducting wire. You'll have a coating of insulating material. That's a terrible diagram, which won't allow the electricity to escape. You never want to touch a bare wire, because bare wire is missing the insulator. Okay, last thing, semiconductors. Some materials are somewhere between being a metal and being a good insulator. And semiconductors behave this way. Normally, silicon is not considered to be a conductor, okay? Silicon is right here on the periodic table of elements, and everything to its left is, pretty much a metal. Everything to its right is pretty much a non-metal. But silicon's sort of in between, okay? It's technically a covalent material. So the electrons are pretty much stuck between the different bonds, holding the silicon together, okay? But some of them are not very, strongly held. In fact, what we can do is we can add impurities into the silicon, such as boron or phosphorus, to add extra electrons or to create missing electrons where electrons can jump. So semiconductors generally are bad insulators, bad conductors, but they can be manipulated with impurities so that they can be made to carry electricity. Now, without going into it, semiconductors, and you look at this part of the periodic table, anything around silicon is pretty close to being a semiconductor. Some form of carbons are semiconductors. Germanium is a semiconductor. Tin is a semi-metal. In one phase, it's a metal, in one phase, it's a metalloid. But on each side of silicon, you also have these materials. When grouped together, they can create semiconductors. So again, without going into too much detail, the semiconductor has electrons that are loose enough that they can be pulled free, okay? And when we add impurities to them, we can create special types of semiconductors. We call them N and P type semiconductors. And when put together, we make diodes and transistors out of them. Charging by friction, that's how we build up static electricity. We rub one material up against another material. Electrons tend to jump from the one material to the other material because some materials have a stronger propensity to hold on to their electrons. We call this a triboelectric effect. And this chart here shows materials which tend to give up their electrons to be at the top of the chart, okay? Asbestos, rabbit fur, acetate, glass, mica, human hair, nylon, wood, fuel, fur. All of these like to give up their electrons. So when I comb my hair, the hair in my head tends to, hopefully it doesn't give up anything else, gives up its electrons and tends to become more positive as I comb it. At the bottom of the scale, we get these materials that like to grab onto electrons. So here we have acrylic, polyurethane, polyethylene, polypropylene, plastics like to grab electrons. PVC, polyvinyl chloride, silicon, Teflon, and silicon rubber. So if I comb my hair, with a brush or comb that has, one of these plastics in it, I will tend to transfer the electrons from my hair to that comb and basically charge it up. So static electricity tends to take place where we do work on some materials. That work is energy that breaks the electrons free. So like you rub a balloon on your shirt, that'll get the electrons to jump onto the balloons. The balloon is an insulator. It's made of covalent material. So once the electrons jump, they can't move. They're stuck on the balloon, and then we can stick the balloon on the wall someplace. I don't know if you've ever tried that, but you take that rubber balloon, it sticks to your shirt, then you can put it up against a wall and stick there. Unfortunately, when clothes are in the dryer, the triboelectric effect causes the material to give up electrons or gain electrons. We'll go back to this chart right here. Cotton, for instance, tends to give up electrons a little bit. Let's see if we can find wool. Wool really likes to give up electrons, but don't put wool in your dryer. That's not smart. Looking at nylon. Come on, where are you, nylon? Some materials will have a nylon mixed to them. There it is. Nylon's right up here. So your clothes, they tend to give up electrons. When they're in the dryer, they rub up against one another. They'll give up electrons to the size of the drum. And then those electrons stick on them. And then everything tends to stick together. That's why we use dryer sheets. Dryer sheets have a special chemical called the surfactant. And surfactants have a positive end and a negative end. They're long molecules with a positive end and a negative end. And they'll pick up the charges as your clothes give them up. And in doing so, they'll neutralize the net charge.
Really? I thought they were only for like softening.
Well,
because that's their main use, right? For softening, right?
Correct. And because you've got polar and nonpolar ends on the fibers themselves, they'll keep the fibers of the clothing from sticking to itself, and that's how they end up softening. Surfactants are actually very, very similar to soaps and detergents, and with a polar and nonpolar end. And clothing can get very coarse feeling if the small fibers just start folding back on themselves. If you keep them long and supple, instead of falling back on themselves where they become very rigid, your clothing becomes soft. So the surfactant does both of them. They soften your clothes. They also prevent static cling. But the wonders of chemistry. Talk to a chemist about that. They have a good understanding of these surfactants. Soap, again, is a fatty acid, which has a polar end on the acid end, and then there's a non-polar end. Detergents, not as sure with detergents, but they have a positive and negative end also. But the surfactants that they use in in these dryer sheets usually have a waxier surfactant, which I think is paraffin, plus they attach a charged end to it. I don't know. I'm not a chemist. Here's something that's cool. This is a Van de Graaff generator, and this uses a triboelectric effect to build up charge. I used to use these a lot in demonstrations, but they build up like 500,000 volts of charge, which for us, it's not the voltage that's dangerous. It's actually the current. They don't build up very much current, but they build up a lot of charge. So if you have like a smartphone and comes in contact with this, you've just done $500 of damage to your smartphone. The high voltage will just destroy anything electronic. So I don't use this demonstration anymore. It's got this big rubber band-like device, which pulls up the charge and it'll deposit it at the top of these spheres right here. And they're really neat looking because if you insulate yourself and you touch them, all the charge ends up sticking at the end of your hair. And your hair puffs up and it's kind of neat. Really large versions of these Van de Graaff generators can be used to demonstrate lightning. And lightning basically is static electricity that builds up on a massive scale. Now, if you take your feet and you drag it on the rug across the floor, you will build up static electricity, and then if you touch something metal, it'll discharge. It's like the Van de Graaff generator. You do work on the loose charge, building up on a conductive surface, and then transfer that to something that conducts the electricity and can take the electricity away. Lightning is a big Van de Graaff generator, but what happens inside of it, instead of a big rubber belt that moves here, what you have instead are huge updrafts from the warm, moist air going higher into the clouds, and then large downdrafts where the rain is pulling the particles down. And although this seems strange that this would happen, that inside the cloud, you have these ice crystals. Draw a little snowflake there to represent the ice crystals, which are rubbing against one another and pulling the charge from the bottom of the cloud, putting a whole bunch of positive charges at the top, normally, and pulling a whole bunch of negative charges toward the bottom. And it becomes a big Van de Graaff generator. So suddenly, when enough charge builds up, just like the Van de Graaff generator will send out little sparks, or just like when you build up enough charge, you touch something metal, this will create a discharge either within the cloud or discharge from the cloud to the ground. So it's remarkable that something as benign as building up static electricity in the wintertime, where you get a little spark out of that, is exactly the same that happens with these thunderclouds. Now, again, you're like, ice. Well, how do we get ice in the summertime? Honestly, the tops of these clouds are very, very cold. They can be, in some cases, many degrees below the freezing point. And what happens here is, as the air goes up into the atmosphere, it expands and it cools. And when we look at weather radar, we're actually looking at the top of these clouds, and the colder they are, usually the taller they are, and the more intense the storm. Okay, so lightning. Lightning, the most common type of lightning, is actually within the cloud. It doesn't do anything. Okay? Strikes from the top of the cloud to the bottom of the cloud or in the middle of the cloud, whatever. The dangerous lightning is obviously the lightning that makes it down to us. When it goes from cloud to ground, if we are part of the electrical circuit, we are going to have a very bad day. So again, I don't know. I've looked at the estimates. Usually about 80 to 90% of all lightning is cloud to cloud. About 10 to 20 obviously is going to be cloud to ground. So that's typically the lightning that we observe. Rare forms of lightning actually happen above the cloud and can only be observed at night. These are called blue jets, and this is where lightning actually discharges upward. Now remember, for most of these clouds, you're building up charge at the top of the cloud. Usually this is positive charge, okay? And you're building up charge at the bottom of the cloud. Usually this is negative. Again, you can build up positive and negative charge anywhere, because sometimes you'll get a really strong downdraft, and this will bring positive charge further down into the cloud itself. But generally, the cloud to cloud and the cloud to ground lightning are more common parts. But we can get discharge, again, upward with these blue jets, where the positive charge will be pumped up into the upper part of the atmosphere. Daughter's just showing me something. All right. The joys of working at home. Lost my train of thought. So we do have these more exotic forms. And this is an actual photograph of one of these blue jets occurring in addition to a sprite on top of it. So there's some you can look this stuff up. There's some really wild forms of high altitude lightning that we just started discovering very, very recently. Let's talk about regular lightning. Again, lightning generation, our cloud builds up charge. Again, ice crystals are rubbing up against one another. No different from you rubbing your shoes on a wool carpet and building up charge. We build up charge within the cloud. The cloud becomes polarized, which means one end is positive, one end is negative. And again, if we build up enough charge, eventually what happens is the charge becomes so great that either the charge will jump inside the cloud or the charge will jump to the ground. And here, take a look at this right here. This is a more realistic representation of what's going on. Here you actually have some positive charges building up at the center of this cloud. So this idea that positives only at the top and negatives only at the bottom is not necessarily true, especially for very, very violent clouds. Okay, lightning. A lightning bolt is actually very, very thin. Lightning bolts are only about 2 to 3 inches across. So if you're thinking about how thick a lightning bolt would be, its diameter would only be about this big. It looks much bigger than that just because it's so bright. But what the lightning bolt is as the electricity discharges, it rips all the electrons off the outer parts of the molecules. It turns the air into a plasma. And this plasma is what we see glowing. Now, if you don't know what a plasma is a fourth state of matter. A gas just has neutral molecules bouncing all about. A plasma will have positive
Isn't it
ions.
in lava?
No, lava is actually just a liquid.
Oh, okay.
A plasma would be something heated to such a high temperature, hotter than even lava. To such a high temperature, twice as hot as the surface of the sun, that's missing electrons. Now, the cool thing here is once we heat the air up to this high temperature, it now can conduct electricity. So as long as there's enough, electrical charge, this lightning bolt will persist. Sometimes it can persist for a second or two. Okay. So when the lightning strikes, we see this big bright flash, this plasma releasing its energy. And because the air has been heated to such a high temperature, it explosively expands, and that's the thunder that we hear. So with a lightning strike, you get a tremendous release of this energy. We see the bright flash where some of this energy is seen visibly. And then we hear this loud sound due to the rapid expansion of the air.
Is it possible to get actually struck by lightning and survive, or do you automatically die?
Oh, you're killing my next my next point. Yes, 80% of the people get struck by lightning. Believe it or not, 80% of the people get struck by lightning live. Okay.
Oh, that's a good
So
thing.
your
I'm
chances
looking forward to it.
no. Neurological damage is not something you want. Yes, most
Oh
people.
no! Oh, that's not good.
Yeah, most people get struck. They live. In fact, there's some park ranger who I think should have changed professions. I think got struck 4 or 5 times. Just get another
Damn,
job.
some luck that guy had.
Yeah, luck. No. I'll post an article about him, but struck all those different times, and oh well. Again, but normally what happens is some of the electricity will damage your nerves and will get you burns. We're not good conductors of electricity. The electricity, it flows so quickly, the energy actually stays on the outside of our body. I got shocked once when electricity hit a tree nearby me, and I'll tell you, it's not a fun sensation. So I can't imagine what it's like getting struck. I was like, I don't know, 50 feet from a tree that got struck, and I felt the electricity go through me because I was, stupidly
Hold on,
touching
you just
something
said
that
you
was
got struck?
metal. No. A tree got struck about 50 feet away from me, and I felt the discharge. Because what happens is when the electricity hits the ground, the electricity fans out in all directions. So you never want to stand underneath a tree because the electricity will go out of the ground and go through you and then go back into the ground. So again, even at a good distance away, even at 50 feet, I could feel the electrical, I could feel the electrical charge. It's powerful. It's powerful, this stuff.
Did your hair stand up?
No. I was just like, whoa, that wasn't nice. It was sort of like if you ever, touch something, a live wire, get a little jolt. That's sort of what it was like. So I can imagine what being struck by lightning is like. Now, here's the thing. The speed of light travels at 300 million meters per second, okay? That's about 1 million miles every second. So we can perceive about 1/10 of a second, okay? So lightning will have traveled 100,000 miles before we would even notice a difference between it striking and the light arriving. So for us, we see the flash instantaneously. Sound, I've got to correct this. It travels a mile every 5 seconds. So again, you can count. If you see a flash, you can count. If it takes 5 seconds for the thunder to arrive to your ear, that means it's a mile away. So again, lightning strikes. Normally what happens is I've actually experienced my hair standing up a little bit when I was out in the field. What happens is, I didn't get struck. what happens is the negative charge of the cloud, or the positive charge, depending, will build up charge on the ground. And as it happens, you'll start feeling your hair standing up. And eventually, when enough charge is built up, then you'll get the discharge. Okay? So if you're ever out in the open and the thunderstorms around and your hair starts feeling like it's standing up, time to get to a lower altitude, just get to a location where you're not out in the open. Tall objects get struck very, very often. There's even another phenomenon called St. Elmo's fire. Pilots see it all the time on aircraft, where you'll see this purple glow because the charge is building up enough to ionize the air around it and produce a very weak plasma. If you see something glowing, this sort of purplish glow during a thunderstorm, get away from it. There's a good chance it could be struck by lightning because it's building up charge. These two campers were hiking up a mountain one day during a thunderstorm, and all of a sudden they thought, oh, wow, our hair's standing up. This is really, really neat. Okay? Yeah. Moments after this photograph was taken, they were struck by lightning. Now, originally, if you can look this up on the internet, I'll say, yeah, 2 brothers killed by lightning strike. I originally had posted that, they were killed, but I saw later a corrected video that they talk about their experience about being struck by lightning. So they must have survived. But again, they didn't recognize that they were building up static electricity. And as a positive charge was building in their hair, okay, the voltage difference between the ground and the cloud was just getting larger and larger and larger. And eventually the lightning struck, and they were okay.
That's so funny. Like, I'm sorry to cut you off, Professor.
No, go ahead.
Imagine them waiting for their friend to take the picture, and then as soon as the flash comes on, the
Boom.
lightning hits them.
Yeah, I don't
Because
think
it's
I had
like
a flash on
the
this
flash
camera.
from the lightning and the flash from the camera.
Yeah, I don't think I had a flash on my camera. Yeah, I mean, again, I don't think they had any adverse effects, but both of them survived, so they were part of that 80%. There is a very dangerous form of lightning. Not all lightning is equal. And most of the time, the lightning is coming from the bottom of the cloud, the base of the cloud. When it hits, it's only having to travel a small distance. So the voltage is not as great. So most cloud to ground lightning is actually of the negative type. Okay, it's coming from the base of the cloud, which is normally negative. Sometimes it can be positive, but it's normally negative. The most dangerous form is when it's coming from up here in the anvil. And the bad thing about this is not only are we talking about a much larger voltage to go from the top of the cloud all the way to the bottom, we're talking about millions of volts. It's also that this anvil can, proceed well in front of the cloud, okay? So if you get hit by a positive giant, your chances of survival are much, much less. And a positive giant is a type of lightning that is extremely powerful and is coming from the top of the cloud instead of the bottom of the cloud. Did you ever hear the term, getting struck out of the blue? Okay, out of the blue. All right. They're talking about a positive giant here. Now, I've exaggerated very much the height of the cloud, but you can actually be in a condition where the storm, most of the storm, I don't know how well I'm going to draw this. Most of the storm is over the horizon, but the anvil creeps out in front of the storm, and these high cirrus clouds don't block out the blue sky. So we see blue sky. Now, the cloud itself is generating all kinds of charge inside of it. And the charge is getting stronger and stronger. And it migrates along the top of the anvil. And as a cold front's moving forward, these cirrus clouds precede it. You're told that if you hear thunder, even if you don't see dark clouds, take cover. Here's the reason why. Very rarely, these high altitude clouds will discharge, and the positive giant, this very deadly form of lightning, can hit you even if the sun is out. Okay? So, rule of thumb, you hear thunder, you can get struck by lightning. And what's happened here is, even though the main part of the cloud hasn't arrived yet, the anvil can still get you. So the term out of the blue comes from these positive giants, which can happen even when the sky is blue. Okay. Each second, there are 50 to 100 cloud to ground lightning strikes in the earth worldwide. This is really cool. You can go to these different weather sites. This is weathertap.com, and they will tell you where the lightning strikes are taking place. And what you'll notice here is they'll even tell you the polarity of the different strikes. Like here, if you see a positive charge, that's a positive lightning strike. It doesn't mean it's a positive giant, it just means that it's a positive strike. Most of the discharges, as you can see, are negative. But along a okay, no problem, got the message. Along a cold front, you will see, these big cumulonimbus clouds building up, and those are the ones that are creating the lightning strikes. So again, typically you have warm, moist air in front of it. You have cold air behind it. And as the cold front comes through, these big clouds build up. And that's normally where we get our thunder clouds, typically during the summertime. During the wintertime, we can get thunder snow. That's more rare because we don't have as much heat energy to create these very tall clouds. But summer day, cold front comes through, that's when we tend to see the lightning. Oops. Again, don't stand near trees. Two things. One, the electricity will spread out in all directions. Also, when these trees get struck, they can explode. What actually happens is the electricity goes through the tree, heats up the moisture inside the tree. The moisture boils instantaneously, and it basically detonates. I shouldn't say detonate. That implies a combustion. The steam goes from liquid water to steam, occupying a volume 1,000 times bigger in an instant, and that creates this explosion of bark. So you can get hurt by a lightning strike even without being near, even without the electricity. Sorry, trying to read messages at the same time. All right. Every time a message comes through, I lose control of this. Electric forces and fields. Coulomb's law talks about the attraction between, I like lightning, spend a lot of time on that. Coulomb's law is an important law that governs how electrical forces behave. Yes.
My bad. I didn't mean to cut you off. Well, but what's a quiver then?
I'm sorry?
A quiver. What's a quiver? You know how we get, I'm not sure if I'm saying it right.
Yeah,
like
I don't know.
We typically get quivers in the summer. Well, it's not like I feel like if it's like a little flash of light. I'm not sure. I'm probably not saying it right, but you could go on.
Yeah, no. There's some really weird forms of lightning. I'm pretty much out of time anyway, so we're pretty much near the end. There's some very strange forms of lightning, like one very controversial um, form of lightning is ball lightning, and we're not really understanding what that is, but that seems to appear during thunderstorms. And rather than coming down as a bolt and discharging, ball lightning's been seen to travel along the ground or travel through walls. So that's sort of on the verge of being sciency and one of these mysterious unexplained phenomena. The quiver, I'll have to look that up. Send me the spelling of that, and I'll try to find out what that's about.
All right.
Coulomb's law. So in 1785, after Franklin had discovered two different charges, Coulomb came up with a equation for the force between charges, and it was very much like Newton's law of gravitation. Which is an inverse square law. The larger the distance, the less the force. If you double the distance, the force drops off by the square of the distance. Now, basically, Coulomb's law says the force between two charged particles will be equal to some electrostatic constant. This is the same for everything. It's 9 times 10 to the 9. Newton's meter squared per Coulomb squared, times the charge of the first object in coulombs, times the charge of the second object in coulombs, obviously named Coulomb, divided by the distance squared. So what Coulomb discovered is, yes, opposite charges are attractive. Like charges repulse one another, but the exact force depends on, first of all, how much charge is on each object, and how far the objects are apart from one another. All right. So let's say we have a positive and negative charge. Each has some force of, I don't know, F newtons, okay? If I were to double the amount of charge on one of these, by Coulomb's law, the charge of one times the charge of the other is proportional to the force. By doubling the charge on one, I double the force. If I double the charge on both, now my force would be 4 times as great. 2 times 2 is 4. If I take that same force and those two charges, and now I double the distance, it's a 1 over inverse square law, okay? Which means that the force goes by 1 over the distance squared. If I double that denominator is squared, I'm now down to 1/4 the amount of force. So there's a lot of similarities between the gravitational force and the electric force. With gravity, everything falls toward something with more mass, the Earth, for instance. With the electric force, anything charged is attracted to anything with the opposite charge. We're out of time. Just quickly, the electric field. The electric field indicates the direction that a charged object with a positive charge would be pulled. So if I try to take another positively charged object, these yellow field lines indicate that that positively charged object will be pushed away. Try to put another positive charge here, it's going to be pushed away. So positively charged objects have field lines that radiate away from them. Negatively charged objects attract positive charges, so their field lines point toward them. I'm rushing, I'm sorry. Electric dipoles are objects that have both a positive and negative charge. Water is a dipole, okay? So at one end, it tends to push away other positively charged objects. At the other end, it tends to attract positively charged objects. That's why water forms ice crystals. It's the dipole force, we call it the van der Waals force, that attracts other water molecules if we cool it down to a low enough temperature. All right, I've abused my time here. Folks,